Okay. All right, guys, be quiet. Thank you. All right, we're going to take a couple notes first. And you guys have some lecture notes at your table, but they are specific to some examples we're going to be doing. So just have those out in front of you. I'll tell you when we're getting there. All right, I'm going to start explaining because as it stands, you already have a plethora of knowledge on equilibrium from Part A, where you were just exploring, like, what the heck is equilibrium, to Part B, where you're looking at Le Chatelier's principle. So we're applying a lot of the concepts you learned already, or you have a generic grasp of, and then we're going to make them, like, really stone, like, really solid. Make the concept solid. All right. So generally we talk about reactions, and every single time we've talked about a reaction so far, it's been to completion, which is just meant as reaction moving forward. And most of the time we just means it goes to completion in all products. Now there was that rare occasion where all products was not quite right. We said there were some leftovers or some excess of reactants left over. What types of problems did we use the word excess? When we talked about reactions occurring, we also had some leftovers of the reactants. Say again? It was a type of reaction where one of the reactants ran out and one of the reactions had some leftovers. Limiting reagent, right? So yeah, like, it still applies because we're saying all the products that could be made were made, but the 100% products and no reactions is kind of iffy. I'm going to say except for limiting reagent problems. So that's what we've always been dealing with. Reactions react, they make products, we move on. And so we've always drawn a forward arrow to indicate that process. We've been doing that just naturally the whole time. What were some evidences, and as you can see here, these are some evidences plus some that you're going to tell me now, that we say indicate a chemical reaction has occurred. I got formation of gas. Okay, what else? Some other characteristics that show a chemical reaction that has occurred. Evan?
Light.
Okay, so light production. Heat production, I heard. What else?
Colors.
Say again?
Okay.
Color change potentially, right? We'd have to kind of look to see if it's a physical or chemical. What else? Right, precipitate, right? Formation of precipitate. And I put pure liquid because the pure liquid idea comes from, like, acid plus base yields salt plus water. And water is a pure liquid, and that's something that can force a reaction to occur. So those are some ideas that we've already explored. We already know all of this stuff about chemistry. Are we clear? Okay. You do not have to write literally every single thing down. If you want to print off my notes, you can do that beforehand. I'm just giving us the general idea that a lot of times we deal with reactions that go to completion, but now we're going to start talking about reactions that. What did you read about in equilibrium yesterday?
Oh, it's closed.
Those are closed and open systems, but what do they do in that closed system? They can. What do you mean do both? Oh, well, they can react forward, maybe in a decomposition, and react backwards, meaning they can reverse the reaction. So that's what our big idea for equilibrium is, that there are reversible reactions out there. So this is actually true for most reactions out in the real world, in your body, in industry. Everything is reversible. But when we're talking about biochemistry, we just kind of keep it simple, which is why we've talked about completion. So with dynamic equilibrium, the word dynamic means constantly changing. As it goes from reactants to form products, and as those products reverse to form reactants. It's a reversible arrow now. That's what I tried to indicate here. It's a reversible arrow. is Kelsey's buddy. Did you already get some? So ways that we know this, or let me back up. The definition that's underlined here, where it says dynamic equilibrium, when the rates of the forward reaction equals the rates of the reverse or the backward reaction. Backward, I'm actually going to start to probably say reverse versus backwards all the time, but that means in the reverse fashion. So the definition of equilibrium is that the rate forward is equal to the rate reverse. And that definition does not tell us anything about the concentrations of reactants and products at equilibrium. It just says that as the reactants produce products in the same amount, products are finishing and making more reactants. So it's just a constant back and forth motion. So what we see now is we actually have both reactants and products left over. It's not just products, like in the first example. But once the formation of products and the formation of reactants equilibrate, or they become equal, we're not going to change the amount of products or reactants anymore. There's no net change. So if I said, all right, I'm going to give Will $10, and he gives me $10, I give him $10, and he gives me $10, and we do that a million times, there's still change happening, right? Like, there's stuff happening. It's dynamic. It's constantly changing. But did anything really happen? No, so net overall, he still has $10, I still have $10, but there were a lot of exchanges back and forth. So that's what it means by no net change, no overall change. What does bracket mean? Concentration, right? Bracket, and if you don't remember that, define that for yourself. Bracket means concentration. So we're dealing with concentrations quite a lot, which is in molarity. All right, so the big point here, though, is that though everything at equilibrium, it just kind of sounds like, oh, everything's just kind of equal. That's not the case. The rates are equal, like the rate forward is equal to the rate reverse, but the concentrations can be different. Did you guys draw those graphs yesterday? You saw the graphs like indicating different amounts. That's what that's referring to. So occasionally, just so you know, you'll see these little arrows, and it's showing you which direction is more favorable. So if the arrow is pointing in a greater fashion to the right, do you think reactants or products are more favorable? Products, right? Reactants over here, products over here. So that just means that the products are more stable. Because stable things exist naturally a little bit better, so that's why we say they're favored. And then the other side, reactants would be favored in this one. Give me a thumbs up when you're good. Some of this ringing a bell a little bit with maybe some of the readings you did. We're going to touch on the K expressions. Okay, so this definition here of the equilibrium constant is really the only thing I want you to write down right now. So K, the equilibrium constant, tells us this. So you have your definition. It's just saying, all right, I'm a value. I'm called K, and that value gives us some information about, is the forward reaction happening faster or more extensively, or is the reverse reaction happening more extensively. It's just giving us a comparison between the reverse and the forward reaction. But we define it as the extent of the forward reaction. So we have numbers that are greater than 1 and numbers that are less than 1. And they tell us two different things about the extent, or they tell us if the reactants are favored or if the products are favored based on the extent of the forward reaction. So you guys can look on the board and maybe even from your web quest think that K greater than 1 represents products or what? So I'm going to say we favor the forward, which means we're making products, right? The forward reaction is making products. So then vice versa, K value less than 1 would show which reaction or which direction is favored. The backward, and I'm not going to say backward, I'm going to say reverse, just to kind of stay with what the terminology actually describes now. So forward favors the reverse. And that means you favor which? Reactants or products? Reactants. And the word favored again means that it's trying to indicate to you if reactants or products are more what? What was the word we just wrote down when I said favored? Emma, it's on your, or no, whose paper? Hannah, it was on your paper, I just saw it. We circled, you circled the little stable, right? So when it says right here products are favored, we're looking to say that it's actually, they're actually more stable, which is actually makes the equilibrium a little bit of a better place to be for reactants and products. So this graph right here, you drew something similar yesterday, but I'm going to sketch it kind of smaller. Now I'll sketch it down here. We have reactants and we have products, but what were the axes for our graphs? You guys remember? Concentration versus time. It's the same as the graph we drew the other day, except now we're looking forward. We're looking a little bit greater along the x-axis. So give yourself a quick sketch of just a graph. Now I have like grid plots. Just give yourself a little L, concentration and time. And let's start off. We're gonna show products are favored at equilibrium. So the other day when we were drawing graphs, we started off with reactants high. We do reactants right here in red. So reactants are going to start way up here. And as the reaction occurs, what happens to the concentration of reactants? Does it go up or down? Everybody. Say again? Reactants, they're reacting, right? They're going to go down, right? Reactants react. They're right here. As they react, they decrease, 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 decrease. So I'm just going to start to show it decreasing. And over time, it's eventually going to stop reacting, or it's going to stop changing, which is now what I'm saying is we're meeting equilibrium. Okay, so there's my line for reactants. I'm going to draw another line for products, but I'm going to start us off before the reaction with 0 products. So where does that start? The bottom, okay, so the 0. So now as these reactants react, what are they producing? Products. So products go up, and as these reactants react, products continue to go up, right? And they continue to go up, and they continue to go up. But as these reactants start to level off, they're really not changing. So this is going to level off as well. I may have leveled off too soon. Hold on. Okay, looks good. So in the end, I can tell when equilibrium has been met because I'm looking on the graph for one key point. Where does it show the reactant and product concentrations are no longer changing? When it becomes a 0 slope, right? When it goes flat. So probably about here-ish, approximately where mine go flat. So mark on your graph where it went flat and put at equilibrium. Because at that point, the concentrations are no longer changing. That's one thing you see. And you should be able to tell the rate forward, which is production of products, should be equal to the rate reverse, which is the production of reactants, because there's no more change, so that means that they were constant at that point. So at that point, we can see who is favored at equilibrium, reactants or products. Who do you have more of at equilibrium? Products, right? Their products are here, and the reactants are here. And so this is showing us not the stability aspect, you can't tell that from our graph, but you can see that there's more of them at equilibrium, so this tells us K is greater than 1 because there are more of them at equilibrium. So now you know how to draw the products that are favored at equilibrium. I want you to draw a reactants that are favored at equilibrium graph. Just draw right next to it. Draw a reactants are favored at equilibrium graph. In the end, who has to be on top? Reactant. So I started this off in exactly the same place. So did we cross lines before we started in exactly the same place? No. No, because we still want the reactants to remain on top. So you easily could have started flipped, reactants on bottom, products on top, but you've had to crisscross the lines. But in the end, overall, the K is going to be showing reactants are favored. And so that means the K value is what? Say again? Less than 1. So K, which is equilibrium constant, is less than 1. Thumbs up if you're good on reading the graphs.
I'm still a little bit confused.
So tell me, is it the understanding where equilibrium is, or is it knowing?
Knowing, like, the reactants favored over the products favored. Like, I'm just confused on why they look like that. Like why that one differs from the one from before.
So this one, really, if I give you a graph, what I would expect from you guys is to identify in the lines, it would somehow tell you who's reacting to products. It would tell you through reaction, or it'd say, like, I'm reactants and I'm products, like we did here. So once you, like, see where equilibrium exists, which is the flat lines, I want you guys to be able to say, okay, products are on top. If products are on top, what do we know about K? Greater than 1. That's it. And if we see a graph that looks, I'm not saying it has to look exactly like this, but if we're reading the graph and reactants are on top at equilibrium, you should be able to tell me what K. Less than 1. That's the minimum. Like, you don't always have to draw your graphs. I would say that you would get a graph and then identify from there as K greater than 1 or less than 1. Give me a thumbs up if you're good with that. All right, cool. Majority rules here. Okay, so just a little bit more on what the equilibrium constant should be, how we would write it. And this was in your web quest too, so hopefully this is a reminder. If we have a reaction, or these little A, little b, little c, and little d, these are all coefficients. What we have to do to write the entire equilibrium constant expression is we simply put K is equal to the concentration of products over concentration of reactants. So who are the products in this generic expression, or in this generic reaction? C and D. Good. So put bracket C, and we're going to incorporate the coefficient now. But do you guys remember how to incorporate the coefficient? It was in your web question yesterday. We put it as an exponent. That's it. So if this were a 2 or a 3 or a 4, that little c would go as a exponent up here. And then we'll do the same thing. We're going to multiply it by the concentration of product D, but raise it to the lowercase d power. Good. So that whatever that coefficient is, it would go here as an exponent. Keep going. What's on the bottom? Concentration of A raised to the power of A, whatever that coefficient is, and then multiply that by concentration of B raised to the little b power.
Are those two separate ones? No, like, is that all one thing?
This, okay, so this is really generic. It's not, you wouldn't have anything to plug in there. I'm just telling you it's products or reactants.
Oh, okay.
So we have to identify the products and we plug the products in. So this is the correct one. This is correct for this reaction. So products or reactants, that's how we calculate K. Okay. So how does that relate back to our calculation, to our K greater than 1? How in the world would K be greater than 1? Who has to be mathematically larger in this expression? Products, right? Big number over small number. What do we get?
Bigger than 1.
Bigger than 1. It's literally all it is. It's just those products, you have more of them, that makes the ratio bigger on top and smaller on bottom. It makes the number bigger than 1. So how would we get K less than 1? Mathematically here.
Like reactant.
A bigger reactant, right? Concentration or a larger number of reactants. That means small number over big number means the value goes down to be lesser than 1. So that math over there matches with this if you actually think about it. Are we okay? Yeah? Most of us say okay. It's called the law of mass action. It doesn't really matter. It's just what it's called. Somebody made up that name. But the molecularity, that word right there, just means the coefficients matter. And that's why we've incorporated them. And then yesterday you guys wrote down what to include and what to exclude. This is the biggest, like one of the bigger points. You will never, ever, ever, ever include a pure solid or a pure liquid if you have like a water or liquid water as a product. You would never include anything pure liquid or pure solid. So that means you only include what? Only include gases and what? One more? Solution, aqueous solutions. So I'll show you guys how to do this with an example in a second. Alright, so once you've written down, never include pure solids and liquids, only include gases and aqueous. Give me a thumbs up so I'm good. And if you remember a little bit of that from yesterday. Some of you guys were breezing through that, but hopefully the second or third time you've seen it, it's starting to click a little bit. We are going to use our little note sheet here. Pull this out for me. Do you see where it says worksheet 1? So worksheet 1 has an example 1 with HF equilibriates. That double-headed arrow you can call equilibriates. So H plus and F minus. I want you guys to write the equilibrium expressions for A and B. The equilibrium expressions for A and B. All right, Austin, get me started. K, which is equilibrium expression.
It's going to equal to the molarity of H.
So I'm going to just put bracket H plus, right? I know it's probably hard to see on your paper, so it's a little blurry. It does say H plus. Okay, what's the power?
1.
1. Okay, so raise to the first power. And then, hold on. Keep going, Aaron. Okay, so I'm going to multiply by the brackets or the concentration of F minus. That is a little bitty minus on y'all's paper too. Raised to the first power. So there's 1 and 1 on those, so that's where we stick. Zane, pick up. So I'm dividing by the reactants, right? So dividing by H, so hydrofluoric acid or something like that, right? Okay, also raise the first power. So now these ones look kind of messy. You don't have to write the ones because it's just a one exponent. So yeah, that's it. Products and reactants. And why did we include all of these? They're all aqueous, right? They're in that category of what to include. All right, let's keep going. And if you can't see this, I'm telling you this now. H2 is a gas. O2 is a gas, water is a liquid. So you might need to write that on your note sheet. All right, take a minute and write that expression out. Yeah. If you have something that's not to be included, put a 1 in its place. Hold its place with a 1. All right, Nandika, get me started. What goes on top? Oh, 1. Good, because this is a pure liquid. Be excluded. Okay? And then, Evan, what goes on bottom?
So bracket H2, and then to the power 2.
Okay, times.
O2 in bracket to the power 1.
Good. So 1 over H2 squared times oxygen gas. Concentrations. Good. All right, so on the next one, I want you guys to attempt that. Notice there's 2 parts. Writing the equilibrium expression, which is always products over reactants, and then the value. Go. Raise your hand if you need a calculator, because I've got to set that for you guys. If you can't read them, I can read them to you. 1.35 times 10 to the negative 2 for HI. 7.38 times 10 to the negative 3 for I2. And 4.56 times 10 to the negative 3 for hydrogen gas. Those exponents are a little small. All right, you guys need to calculate. You need to try by yourself instead of just looking up on the board for me. Ladies. Yes, I'm talking to both of you. Yeah, show that process to show what
So a
lot of you guys are not putting your denominator in one big hunk of a parentheses. You need to put double up or triple up parentheses, whatever you need to do to verify that the denominator is in the denominator. I heard like one answer that was correct. Is it 2.5.4? Yes. Okay, answer, ready. 5.
Yeah.
All right, I need everybody to show me that on their calculator. Fix your stupid calculator mistake you did. Fix it.
Well, I'm just talking, I was just speaking. Oh my God, just put much on. Now
I got 2.94.
yeah, it's times 10.
All right, give me a thumbs up if you got the correct answer. All right, you see those calculators, they're not as far as you think they are. You're the user error. Okay, that's you.
Oh, I got it.
Okay. So another thing to write down here is I want you to tell me the K. What? So it's greater or less than 1?
Greater.
Greater. So what does that mean to us?
Oh.
So now I'm going to write 2 things. Products are favored. And that means to us, like if we looked at it graphically, what would we see? Products favored means what at equilibrium? Who has a higher quantity at equilibrium? So more products at equilibrium. And then another thing, Mackenzie, what do you notice about my answer? What? No units? This is a beauty. It's unitless. Unitless. K value is just a value. It's not a measurement. So there's no unit on it. What? Okay. So after all those units, may I go forward? Okay. So we can't do 3 yet. Can't do it. Okay. I want you to write the equilibrium expression, meaning just like the setups, no numbers, for 1, 2. Hold on. Let me make this a little bit easier to see. Can you guys see that? Let's do 1 through 4 first. You can write it on your notes someplace. Go. Equilibrium expressions.
That's not. It's true. It's a solid.
Okay, the products are all over the Alright, scrolling down so you can see some more. I'm not going all the way, just stay like 2. I'll go back. You got a couple more.
No, but like,
There we are. What do you mean?
that doesn't make sense. What, Brian?
YouTube now.
So keep that whole compound like this guy. That's one big entity. And then the you get crazy. Put the whole thing. Raise to the 1 power. All right, what number are we on? Five. I'm just one. All right, I'm gonna scroll back up a little bit and then start reviewing these. Are you getting the hang of it? Yeah. Are you think you'll no, there's no patch. You're good. Okay. So I'm gonna write over here. So Jasmine's table, get me started. Number 1, get me started. Evil. Respect. Thank you. K is equal to bracket. And then H2. H2 to the second. Thank you, Jasmine table. Keep going. O2 over. H2O to the second power. Those are all gas, gas, gas. We need all of them in our expression. So gas, 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 all gets involved. All right, next, number 2, the carbon example. Anthony table.
So we started off with the H2O on top.
H2O.
No, we did not.
No? Okay, there's no H2O there. Okay.
We start off with CO on top.
CO on top
H2O next to it.
times H2 concentration.
And on the bottom, H2O.
H2O. Well, what about the carbon, guys?
We don't include it
Why not?
because it's solid.
Because it's a solid and nobody cares about the solids. I know. Okay. Halley's table. 3. K is equal to. Halley's table.
Big bracket H2CO3 over CO2, and you leave the water alone to liquid.
Pure liquid. We're excluding it. Good. So that's just one product over one reactant. Cam's table. Number 4.
K bracket Mg2 plus
Good. We got the ion charge in there. And
times bracket Br negative.
There's a 2 after the
2 exponent. Yep. Over. You put over 1. You can just not put anything there, period. You could have just put Mg2 plus times Br minus squared, not over anything. Are we okay? All right, Will's table, number 5. 1. How? solid, and liquid. So we exclude everything. All right, so moving on. Ready? So we're gonna do another calculation, but a little different version of it. And I printed, if you look where it says calculations involving equilibrium constant example, do you see that on your paper? All right, so you guys are gonna do, do one first, and then I'll see if I want you to do the other two. Go ahead and do one first. It's on your paper. Do 1 and 3. That's it. 1 and 3. Write your expressions, write your workouts, don't calculate. One and 3 are the two that you're doing from this section. They are the same. On 3? Yeah.
We're working on it.
Okay. Kelvin, like it's just telling you a temperature it's established at. It doesn't matter. Wait, it's Kelvin is just our temperature. It's just saying what temperature is occurring at. That's all. No importance.
No, that's fine.
I mix it
All right, let's talk about number 3.
Yes, please.
Okay, just wanted to make sure you got started without me there. All right, so we have our k expression. Are we okay with that? We had a squared. That was the only one thing that we had to do. Random thing, yes? Okay, we can set up a k expression for anything now. We exclude liquids and solids. Okay, so setting this up, plugging in the 0.8 for the methanol, and the 1.42 for the carbon monoxide. It asked us to solve for H2, so we don't have anything to plug in there, so we put X. We give them set up.
Yes.
Okay, so that don't forget that is squared. So if you want to rearrange this all for X, how do you get X out of the denominator? Multiply it on both sides, right? So you multiply it up over here. Let me get a different color, sorry. You multiply it up over here, and you multiply it, as itself, but it's going to cancel itself out. That's why I said the second little expression up. I left the 0.818, the 1.4, but then this is what we kind of established by multiplying X squared up. And then we want to isolate X further. So isolating X further, what do I need to do with this? Divide by 1.609 on both sides. So when we divide by 1.609 on both sides, we end up canceling it out over here, but we divided, so therefore it's below, it's in the denominator here. X squared is left. Then I need to continue. So I just went ahead and calculated to make my math look a little bit better, a little easier. And who got this far? What? All right, a lot of us did. X squared is still not to its final calculation yet. So then how do I get from here to here? Square root of everything, right? So square root both sides. So square root of 0.36 blah 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 is 0.602. You guys double check my math, right? Double checking my math. Okay. So this is the concentration at equilibrium of hydrogen gas. So it's not more difficult, it's just algebra. You just have to kind of focus on the math rearrangement for a moment. Thumbs up if you've gotten down your work that you need. Okay, go ahead and finish that up for me. We're going to do one more. All right, so you've had a chance at least to follow through with some of the math. All right, so in terms of setting up K, knowing what K means, calculating K, can you do it?
Yes.
Yes. We're going to do some more examples on Monday that are just include a little bit more elaborate examples, but we're not going to do them today because I'm not going to wait till Monday. So here's what you need to know, that this is your curriculum. You know how to define equilibrium.
Yes.
The rate forward equals rate reverse, right? Okay. We can distinguish between the fact that something has equal rates versus equal concentrations. If they have equal concentrations, that graph would end with them having merged. I didn't draw that graph earlier, but they would merge. Now, they can still be at equilibrium, but does equilibrium mean that everything's in equal concentration? Yay or nay? Equilibrium doesn't mean everything's in equal concentration. No, it just means I've stopped like net changing those concentrations. They can be different as we've seen through calculations and through graphs. Yeah.
Is that like on the other one, number 5, where it was just 1?
Yeah. Okay, assuming that the concentrations work out, so the math works out to be 1, that could be an example like this. Yes. And then we know how to explain or give the equilibrium expression for a reaction. That we know how to write the K expression.
Yes.
Yeah or nay? Okay, good. So we're gonna talk about like the effects of stresses, which is Le Chatelier's principle, but I'm gonna show you a video first before we do that. Okay? So give yourself a stretch break. Get up and see somebody. Talk about what you're gonna do this weekend. You have a minute, or not. I mean, do whatever you want to do.
Is that a lot of work? This project hasn't
All right. So come back to me. Come back to me. Okay. So you have Le Chatelier's principle. Write this as like the next header on your notes. Le Chatelier is its French, but Le Chat principle is kind of how we abbreviate. Le Chat, it's not chats. Le Chatelier's principle. It doesn't really matter as long as you know what your principle is. We're good. You spell his name wrong, it's fine. Okay, so Le Chatelier's principle is going to explain to us once we're at equilibrium, what if we change something? What does it do to the equilibrium? How do we know that? How does it shift? So we want to know about shifts, which is what this video is going to start to explain.
Catelier's principle, which explains what a system at. In this lesson, you will learn about Le Chatelier's principle, which explains what a system at equilibrium does in response to stresses. Let's return to our original example of you digging a hole and your friend refilling it simultaneously. If you start digging at a rate faster than refilling, the hole gets larger. In order to maintain a constant size of the hole, your friend must work harder to fill it faster. Following on the same idea, when a chemical system at equilibrium is stressed, the system works to restore equilibrium. This is Le Chatelier's principle.
So you have Le Chatelier's principle written on paper. What did she say it was?
It's
So it's when a stress is added,
It adds more stress to balance it out.
it doesn't give it more stress. It tries to fix itself to get back to equilibrium. Okay, so what happens when, well, that's the question. Huh? So Le Chatelier's principle is once the system is, I'm going to put stressed in quotes here. The stress is coming like 5 or 6 flavors. So once it's stressed, what's it going to do? Okay, I'll say it fixes, I like y'all's words, fixes itself to get back to equilibrium. Right. So just like if you're happy, thank you. You're happy and you're well established, you're stable, and then all of a sudden somebody stresses you out, you gotta get that person out of your life, right? Get out of your life, right? So you gotta get out of your life. So your job is to reestablish yourself back to your equilibrium. If you don't get enough sleep on Wednesday and you are cranky, you are not at equilibrium. We get back to equilibrium by getting more sleep. 2-hour delay, right? Okay, here we go.
The stresses are when a chemical
So you're writing down the stresses now. Get ready. Shush.
system at equilibrium is stressed, the system works to restore equilibrium. This is Le Chatelier's principle. The stresses are changes to the concentration of either the reactants or products changes to the pressure, although this is only applicable to gaseous systems, changes to the temperature. Let's examine a hypothetical reversible reaction at equilibrium where reactant A reacts with reactant B to form product C and product D. If we added more A and B, the system becomes stressed and is no longer at equilibrium. To counteract the stress, the system forms more C and D.
Okay, so you see this little balancing beam, right? They said you added too many reactants. The stress is too many reactants. So what it has to do is it finds a way to shift right or shift left. Those are the only two ways to fix equilibrium or fix the stress. So what that means is if it shifts right, who's it making more of? Products, right? And if it shifts left, who's it making more of? Reactants. Well, if the problem is, oh no, I've got too many reactants, do I want to make more reactants? No. That's going to exacerbate the stress. It's going to be like a bad thing. So how do I get rid of reactants? You can't just add more products. Like the only two options you have is shift left or shift right. If you shift right, you say reactants react. As reactants react, they make products, and we've solved our problem. We've gotten rid of reactants by the nature of going in the forward direction. Give me 2 thumbs up if you got that. Like you heard what I said. Like you know it. Okay, that was only one example, but I'm going to keep explaining, okay?
In order to remove the excess A and B. The equilibrium, therefore, shifts to the right. If we added more C and D, the system becomes stressed and is also no longer at equilibrium. So to counteract the stress, the system forms more A and B. Therefore,
meaning it shifted left. So too many products. Oh no, I gotta get rid of them. Which way do I shift? To the reactant side, towards the left, to say products react in the reverse direction. So that means a shift left.
Equilibrium shifts to the left. What happens if we remove C and D as they are being produced, or if the concentration of C and D is decreased?
Okay. Oh no, I don't have enough products. Which way do I need to shift? To the right to make more of them, so we're back at equilibrium.
Please pause the lesson to think about this and resume when you are done. The system is now stressed and no longer at equilibrium. To counteract the stress, more C and D are produced, so equilibrium shifts to the right. When concentration increases, equilibrium shifts to the opposite side of the reaction. When concentration decreases, equilibrium shifts to the same side of the reaction. Changes in pressure. The stress to a system at equilibrium is only applicable to gaseous systems. For this stress, we will examine another hypothetical reaction at equilibrium, where reactant A reacts with 2 moles of reactant B to form product C and product D.
Can you write that reaction down? Put gas, 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 gas for all of those. Gas, 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 gas. So A gas plus, so like gaseous A plus 2 moles of gaseous B yields, or equilibrates, sorry, the double head arrow equilibrates to gaseous C and gaseous D. All right, so A, 2B, C, and D. A, 2B, C, D.
An increase in pressure means that there is a decrease in volume, so there is less space. Equilibrium will shift to the side of the reaction with fewer moles. In our example,
all right, so, Emma, we get the lights ring. All right, so they just mentioned one thing that we probably missed it. All right, so we have a reaction, right? It's all gaseous. And it said if you increase pressure, it's going to cause a shift because we are not at equilibrium anymore. So this is all happening in like one big closed container. You've got A and B and C and D all in here. They're just floating around together. Because at equilibrium, who's present? Reactants? Your name? Some of both, right? Some reactants and some products. So we have them all in this closed system together, just hanging out. So all of a sudden, what if I make the whole system smaller? It's smaller, right? Smaller in volume. Well, smaller volume
Do you remember your Boss Bear? Hey, Boss Bear, look it up. Okay, decrease your volume. What did you do to pressure? You decrease because the particles are hidden inside of containers like quite often here. So the problem is, oh no, I have increased the pressure, oops. Now I've got to shift to a direction that's going to alleviate that pressure. So, you with me, ladies? So I have too much pressure. I'm going to shift to one direction that alleviates that pressure. How many moles of gas do I have over here on the reactants? 1 plus 2 is 3 moles of gas, right? We have to have gas to talk about pressure of solids, which don't cause really a lot of pressure. How many moles of reactants are in the products? 2 moles of gas. I want to shift to the side that's going to alleviate pressure. Which side do you think that would be? To the 2 moles, right? Because that's going to give us a chance to say, okay, less stuff, less collisions in the container wall, less pressure. So if I increase the pressure on this system, it's going to find a way to decrease pressure, which in this case would be a shift right, because I want to go to the side with 2 moles of gas, not 3 moles of gas, because 3 moles of gas is going to be what pressure? Increase it would exacerbate our pressure problem, and the class would explode. Question? So what it means to shift is, let's say I had equal, just say I have equal A, B, C, and D here. If I shift right, it means I'm going to produce more C and D. So I can add some more C's in here and B's in here. And then what is essentially the A's and B's would decrease. So I'm not going to take them out, but I would decrease them in concentration. That's it. So the shift just means produce more or produce or consume some. That's it. Okay. So let's do some practice examples with this. And actually, let's finish this video real fast because the lights back off for me. Thanks. All right, pay attention with me. You guys are getting sleepy.
Equilibrium will shift to the side of the reaction with fewer moles. In our example, an increase in pressure will cause equilibrium to shift to the right, since there are fewer moles, 2 moles compared to 3 moles on the left. A decrease in pressure means that there is an increase in volume, so there is more space. Equilibrium shifts to the side with more moles. So in our example, equilibrium shifts to the left. So an increase in pressure favors the side with fewer moles, and a decrease in pressure favors the side with more moles. In our next lesson, you will learn about how a system works to restore equilibrium in response to...
Okay. Now, Emma, one more time for me. Thank you. All right, so the stress they did not mention was temperature yet. We're going to talk about that one now. Do me a favor, turn to the back of your lecture notes. We're going to do some of these practices. All right, so I'm going to start with the practice examples, and I'll go back and fill in some blanks as we need to. All right, so you have this reaction. Nope, you don't have this one. This is my lecture example one. I'll do your practice ones in a second. Write down this reaction. N2 gas plus 3H2 gas equilibrates to 2NH3 gas and 92 kilojoules of energy. Okay, so what we have to do with this first sample, or this first part, I just want to call it A, write down for yourself increase heat. Okay, that's your stress. So the stress is increasing in temperature or increasing in heat. So that's the problem. I want to get rid of that problem, correct? Okay, so what we see here is that, is this an endothermic or exothermic reaction? Okay, so loud and proud. Exothermic. You see the energy is being released. Energy is being released, so this is definitely exothermic. So, well, we can kind of say this, but we would never say this out loud. We can think it is heat's acting as a product, because where is it at? In the products. Well, we know it's not really just any old product, it's energy. It's kind of different than the normal products we produce. So heat is acting as a product. If I heat the system, you're essentially saying to yourself, oh no, I've increased the products. That's what I'm writing here. I've increased the products. So which way will that shift if I've increased products? In the opposite direction, right? So we're going to shift left. because I want to reduce products, and that will cause an increase in reactants to reestablish equilibrium. So this is why, as I increase one side, I want to get rid of that stuff on that side, so I'm going to react it in the reverse reaction, which to us is just a shift left. Yeah.
So energy is on the products, then shift left.
If you increase energy and it's on the products,
What do you mean
well, it says we add heat. We heated the reaction. If it says we cooled the reaction, that would mean we were removing energy. And so if I remove this energy, oh no, I don't have enough of it anymore. I want to make more, so I'm going to shift to the right. So it depends on the stress. It depends on the scenario. We're going to do some more, okay? Increasing pressure, okay? So, oh no, I've increased pressure. I want to do what with pressure now to fix it? Relieve pressure. So I want to choose which side of the reaction will relieve pressure. So what do I need to do now? I want to count moles. Good. I'm putting like your prompts for yourself. If you've increased pressure, you want to find a way to reduce pressure. Okay, so then you have to count moles of what? I'm not sure what they're doing. I'm thinking they're just moving. They're just moving things. No, I'm not going to worry about that. Okay, so I need to count moles of gas. How many moles are in the for reactant side? 4 moles of gas. And this side, 2 moles of gas. So once I've counted moles, I need to figure out which way will alleviate pressure. Shift to the right, because I have 2 moles of gas versus 4 moles of gas. 4 moles of gas will explode the container because it's so much pressure. 2 moles would have alleviated the pressure we caused. So the first one is a shift left, the second one is a shift right. Okay, let's finish this example and then let's see if you can do what you're doing here. All right, removing NH3, which is a, yes, I want to know if it's reactant or product, which is a product. So we have removed a product. Oh no, I don't have enough product. Which way do I go?
Right.
Again, so I'm going to shift right to make more products. My problem was I removed product. Okay, so you're always righting your wrong. You're fixing your stress. You're removing it or you're adding it to fix whatever was done. Adding excess H2, where's that? Okay, so I've added, that's not right.
This is the bells one.
I know, I don't know why they're back on. They haven't changed the schedule, whatever. We get out in 10 minutes. Added a reactant. All right, so if I've added a reactant, oh no, I've got too many reactants, which way? I don't want to go left, I'll make more reactants, so it exasperated. Shift right. Okay. One more. You guys do this one. Shift right. All right, hold up your left or right hand in 3, 2, 1. Left or right hand. I didn't say shout it out.
Oh, my bad.
Left or right hand. All right, hands back down. Shush. So I heard Anna, I think, say, decrease the volume does what to pressure? Okay. Increases pressure, ... I got to count moles because the problem is, oh no, I've got too much pressure. I want to find a way to decrease pressure. So when I counted moles, there were what, 4 moles on one side and 2 moles of gas on the other. Which side will give me less pressure? Shift right. Yes. Okay, so now I want to see if you can do this. You guys have. No, you have like almost 10 still. I want you guys to do 1 through 4 right here. All you are writing is shift left, shift right, or if you have the option, take it through. No shift.
No shift left or shift right. They both have some on both sides.
Teachers and staff, please quieten that bell. Please stay on the schedule, on the 2-hour delay schedule, which was sent to you this morning by Ms. Blakely. Thank you.
Are these no shades? Right.
The minute goes right. That's you. And you.
There's two on one side.
I want to start
I'm gonna give you some clarity here on that first example. 3, 2, 1, back to me. Shh. Okay, we said for the first one, shift left because essentially you have added a product. Shh. you've added a product, you have too many products at this point, you shift the opposite direction, because as you shift left, it consumes products and it produces reactants, which is why it's going to go to the left. Decreased volume causes a no shift, because there are how many moles here? 2, and how many moles here? No way will alleviate it, so nobody gets the win here. Adding HCl, which is it's a product, so if you've added a product, which way does it shift? Left, because it's going to go away from the products. Adding sodium chloride. No shift. Do you see sodium chloride up here at all? Nope, so it's not relevant to our equilibrium system, so it's a no shift. And removing chlorine gas, because I have now decreased my reactant. No more reactant. I need to make more reactant, so I'm going to make it by shifting to the left. Okay, good. So, we have a couple minutes left. You guys have 1 through 4 to attempt, which is, we'll check these on Monday. So you have 2, 3, and 4, and you have your blue, which my ideally yesterday was what? Half? The first half or the second half? Mix it all up. Okay. You take a minute to try to finish where you are. We leave in 2 minutes, okay? Finish where you are.
For temperature, because temperatures are lower than it's going to be, you think about when you think